Christoph is going to get the stage. Thank you.
Thank you, Andrea, and thanks everyone for coming. Thanks for the organizers to give me the opportunity to talk about some of my favorite problems here. I plan to say that this talk is going to be different from other talks in the workshop, and now everyone today has said that already somehow. But my talk is maybe even different from everything that also happened today. Yeah, everyone is unique, I guess. So I'm going to talk about ReLU networks. So if you were hoping for graph neural networks, I don't have many of them for you. But what I do have for you is at least some graph problems appearing in the end. But the main object I like, and which will be very relevant, is polyhedral geometry. So Polyhedra in the end. But OK, what is this about? I mean, let's talk about a very simple thing, namely a single neuron. I want to define that properly because we're going to use it. So what does a neuron do? I mean, it's a ReLU neuron, so we have this ReLU activation function. We take the weighted sum of the outputs of the previous neurons, we add a bias, and we put it into our ReLU, and this is the function computed by a single ReLU neuron. OK, we all know this. If we look at the graph that's computed by such a ReLU neuron, let's say on 2 inputs, it would look like this. So we have this affine transformation by the weights and the bias, and then it gets flattened out where the ReLU is negative. OK, so here we already see something nice. So the ReLU neuron somehow divides the input space into 2 half spaces, on each of which the function is affine. Yeah, this is going to be relevant later. OK, so if we take these ReLU neurons and we put them together into a network that's usually acyclic and layered, then it looks like this, and this is a ReLU network. So it would map some function. It would represent some function mapping from R2 to R3 in this example. Some specific things I want to be clear about. I don't have bias. I don't have ReLU activation functions at the inputs or outputs. So this has 2 hidden layers. Yeah. We can also represent this as a alternating composition of component-wise ReLUs and affine transformations Ti, like this. And just to be clear about that, so as I said, this would be 2 hidden layers. But I would call this depth 3, because it has like 3 affine transformations here. There are people like this plus minus 1 on the depth. This is like some people use it like this, some other people use it like that, and I find it very confusing. So depth is 1 more than hidden layers for me. And the size would be the overall number of ReLU neurons, so not counting input or output. Good. Why is this so important? This is so important because I'm going to talk about expressivity. And what does expressivity mean for me? It means if we fix an architecture, like the depth or the size of the ReLU neural network, what functions can we represent? So what if we decide, OK, we want to use depth 3 neural networks, what classes of functions can we represent with them? And yeah, by the way, if you have any questions, I'm happy to take them during the talk. Yes?
Does it also work if you just drop out edges?
If you drop out edges, I mean, the question is what does work then, right?
Your theory.
I mean, yes, because it's, I would say the simple answer is yes, because you can just set the weight to 0 and that would be equivalent to that. Yeah. Yeah. So in a way, what is, if you want to phrase this in a different way, this is viewing ReLU neural networks as a model of computation, similar to what people do in circuit complexity, right? So we have, in circuit complexity, would have Boolean gates and then inputs and outputs, and they would represent some Boolean functions. Here we have real functions, and it's really, like I'm really talking about real functions, so I'm not talking about any bit encodings or anything. So I have real valued functions, and we have ReLU neurons instead of some Boolean gates. And this is maybe more closely related to what people call arithmetic or algebraic circuit complexity. OK. Also, obviously, this is related to approximation theory, like universal approximation theorems and everything. In a way, I'm looking at it in a more fine-grained way because I want exact representations. Of course, in some cases, you can also relax this and then maybe use results on exact representations to say something about approximations. But for the purpose of this talk, let's really focus on exact representations, because this already has enough interesting problems to talk about, I would say. OK, so that's the stage. Any questions at this point? Let's go with a simple example. So I want to express the maximum of two numbers, OK? How can I do this? Well, I want to have something like a ReLU here, so I subtract y on both sides of the maximum. I obtain maximum of x minus y and 0. And then, of course, I have to add the y in the end again to have the same function. This I can represent with a ReLU neuron that gets a positive connection from x and a negative connection from y, and then I feed it to the output. And now what I would like to do is add a skip connection from y to the output, and I represented exactly this maximum function. That's fine. If people don't like skip connections, it's still not a problem, because we can split y into a positive part and a negative part. So if y is positive, then this path will exactly represent y, and the other path will be 0. And if y is negative, then it's exactly the other way around. So propagating the identity is not a problem by just using two neurons for that. OK, so we have a simple one hidden layer ReLU neural network representing the maximum of two numbers. Let's get a little bit more fancy and compute the maximum of 4 numbers. How do we do that? Well, we compute the maximum of 2 of them and of the other 2 of them, and then we compute the maximum of the 2 maxima. How many hidden layers do I have here? What would you say? 3. Other guesses? 2. It's 2, because I said we don't have activations at inputs or outputs. These are only inputs or outputs, so we can combine the linear combinations before and after this layer, so this is not actually a hidden layer. Yeah. Of course, we can now again copy this network next to each other, add another maximum network on the output, and that gives us a maximum of 8 numbers with 3 hidden layers, and so on. And to put it the other way around, logarithm to the base 2 many hidden layers are sufficient to compute the maximum of n numbers by this construction. OK, this is our first nice little expressivity result that appeared in that way, I think, in some ICLR paper 2018. Yeah. But it's just a cute little example, right? We are computing the maximum of a bunch of numbers. Can't be too fancy. So let's talk about general ReLU neural networks. Yes, there's a question. That's an upper bound?
I mean, this is like you can do it with that number, but
yes, exactly.
It doesn't say that you cannot do it with less.
Exactly. That's correct. It's an upper bound.
But do you have a lower? Is there a lower bound?
Be a little bit patient. I will talk about this. Yeah. OK. So in general, a ReLU neural network, like every neuron computes something continuous and piecewise linear, right? Just because the ReLU is continuous piecewise linear, linear transformations are trivially continuous and piecewise linear. So if we compose this, it stays continuous and piecewise linear. What does it mean in multiple dimensions? It means that you take your input space, subdivide it in some polyhedral regions, and it's linear on each of these polyhedral regions. Yeah. OK. Now, the cool thing is that the converse is true as well. So give me any continuous piecewise linear function. I can give you a ReLU neural network computing it. Exactly, on Rn. How does this work? You use this cute little structural result about piecewise linear functions from Wang and Sun from 2005. What does it say? It says an arbitrary function defined on Rn can be written, like continuous and piecewise linear, can be written as a linear combination of maxima of a bunch of affine terms. OK, and the clue is, like this linear combination can be big, this p in this sum can be big, but each of these maxima has only n plus 1 many affine terms. That's going to be important. But first, no matter how many terms you have here, I mean, what you now can do is, yeah, you just implement the maximum in the way we just saw it. You combine it with these linear combinations. You already have a ReLU neural network computing the function. So this structural result basically gives you the ReLU neural network. And now the point, the observation that these are at most n+1 terms here also gives you a bound on the depth of that ReLU neural network. Because what can you do? You can just take all these maxima and you implement them in parallel. Like this can be very wide then, but it will not be deeper than the computation of one single of these maxima. And this is a maximum of n+1 many terms, and we just saw it how to do this in logarithmically many layers. So in other words, what you can conclude from this result, and this is the ICR paper I mentioned earlier, is that every continuous piecewise linear function defined on Rn can in fact be represented with a ReLU neural network that has logarithmically many hidden layers. Yes?
Isn't the second theorem a simple conclusion of the first?
Yeah, it is. Yeah, I mean, you need this maximum construction, which I showed you earlier. But then, yes. Yeah. I mean, this paper also has other results. It's not like this is the only result of this paper.
Like 4 people to do it.
Yeah. I mean, but still, I mean, it's kind of the standard reference to say that a continuous piecewise linear function can be represented by a ReLU neural network. So I think this has some significance, even if the result basically is a pretty quick conclusion from this result, which is deeper. I mean, this is a little bit harder to show. All right. Good. What is the obvious question? And this is what was asked earlier. Can we do better than this logarithmic depth? Obviously. And the other complexity question, yes?
So in the previous result, the first one, this 1-7 result,
Yeah.
so the P depends on the distributive complexity of F?
Yes. So you can prove bounds on P that kind of depend on the number of pieces of F, for example. And the dependence is not so nice. So it's what is it? So if you have q pieces, then it's something like q to the n squared or something like that, if n is the dimension. So, and I actually don't know if this is optimal in some way, but this is an upper bound on this p, which is not very nice. But there exists an upper bound at least. Yeah, but the more, like the intuition is the more pieces F has, the higher this P will be, even though if the pieces have a nice structure, then this doesn't necessarily need to be the case. Okay. So this first question is, can we improve this depth here? Or is it maybe the best we can do? And then, as I said earlier, this is kind of like a model of computation, and if you ask complexity questions about a model of computation, you're usually interested in the class of functions or problems you can solve with polynomial complexity. In this case, this would translate to what classes of functions can you compute with polynomial size neural networks? That would be the other question I would like to talk about. Okay. Let's go. Let's go. Is logarithmic depth optimal? And yeah, the first observation is, I mean, basically, I guess this was maybe already clear, but they write it down as a theorem here, is that we only need to understand the maximum function. By this Wang and Sun result, which we just discussed, basically everything boils down to the maximum function. And the maximum function is the most complex function to represent with a neural network in that sense. So from understanding all the continuous piecewise linear functions, we're coming down to understanding how many layers we need for the maximum function. And that's all we need to know. It seems much easier than understanding this wide zoo of continuous piecewise linear functions. Yeah, that's what I just said. We only need to understand the maximum function. Good. So let's do it. Let's understand the maximum function. We saw an upper bound. We saw logarithm with the base 2 is sufficient. And I have a lower bound for you. It's not a very strong lower bound, but it's a lower bound. And what does it say? It says that the maximum of 3 numbers I can set one of them to 0, this doesn't matter much. But the maximum of 3 numbers cannot be represented with one hidden layer. So such a neural network would not be sufficient to represent this function. So why do I draw the function like this? This is basically a view of the input space, and the function has 3 pieces. In one piece, the function is 0 because the maximum is 0. In one piece, the function is equal to x1, and then the third piece, the function is equal to x2. So why can I not represent this function with a one hidden layer ReLU neural network? If you think back to this 3-dimensional plot that I showed in the very beginning, I said every neuron divides the input space in 2 half spaces. So it's one line in 2 dimensions, it's just one line. Now, if you have a one hidden layer ReLU neural network, it's just a sum of several of these neurons. So basically, like this set of pieces will always be the cells of a hyperplane arrangement for a one hidden layer ReLU neural network, or line arrangement in R2 even. But this is not the line arrangement. We have these half rays here. So you cannot represent this with a one hidden layer ReLU neural network. OK, yes?
If you say your domain is only some compact set, so
yeah, I mean,
that make everything different? Like here it seems like it would work, no?
In exact, no, I mean, if your compact set contains the origin in the interior, exact representation still doesn't work. You still have the same hyperplane argument.
Could you translate it and translate it back? Like you could.
Well, I mean, sure, if you want to represent a patch of the function that does not include the origin, then it should probably work. But I mean, otherwise this translation thing still doesn't work, I guess. Maybe I can convince you later to full extent, I don't know. OK, so what other lower bounds do we know? I mean, this is a very easy lower bound, but at least it says that one hidden layer is not sufficient for exact representations. And here it is. We don't know any other lower bound. So in full generality, at least. I mean, I've worked on this for a long time, and there are special cases where we know lower bounds. But in full generality, we don't have anything that shows that there exists a single function for which 2 hidden layers are not sufficient. OK, so it could be that 2 hidden layers are enough to represent all the continuous piecewise linear functions. But maybe it's not. Maybe it is. I don't know. Together with this upper bound, there's a gap between 2 and logarithm to the base 2. And that used to be the case until very recently, as I will tell you now. Or maybe, OK, before I come to that, one quick thing. So even for the maximum of 6 numbers, where we, again, I set one of them to 0, but this doesn't matter much. Even for the maximum of 6 numbers, we don't know if 2 hidden layers are sufficient or not. So we know that 3 are sufficient, but we don't know if 2 could be sufficient or not. OK. So here's the.
That for 5, you know that 2 are sufficient.
Exactly, and that's very new, and that's what I'm going to tell you now.
OK, I'm sorry.
Yeah. Yeah, I mean, I was kind of trying to make some tension, but I guess it didn't work that well. But never mind. So a couple of years ago, when I was really annoyed by this logarithmic upper bound, which didn't seem to be able to improve, I thought about it together with some clever other people, and then at some point we were like, OK, this must be the optimum. There's no way that it can be better than logarithm to the base 2, and we were bold enough to phrase it as a conjecture. And yeah, the conjecture was even published in some Nuremberg paper. So I guess people believed that our conjecture could be reasonable. Yeah, so then, I mean, we still worked on this. We tried to prove it. We proved it in special cases. Like one of my favorite special cases, if you restrict the weights of a neural network to be integers, then the conjecture is true. So then, like, if you think back to the construction, they were just plus 1s, minus 1s, basically. If you put this together, it's everything stays integer. So we were able to prove that if you stay integer, then logarithm to the base 2 is exactly the right answer for the number of layers you need. But yeah, I mean, without such assumptions, we weren't able to make any progress on this conjecture. And then, as I said, since this year, we know the conjecture is actually false. And the smallest counterexample is exactly what you said. The maximum of 5 numbers can be represented with 2 hidden layers. That's what we were able to prove. Or more generally, the maximum of n numbers can be computed with logarithms of the base 3 many hidden layers, basically. Okay, I'm going to show you a little bit of intuition how this construction works in a bit. But yeah, so this was very surprising to me because, I mean, we defeated the conjecture I made myself a couple of years ago. And I have I have no clue what to believe now, to be honest. Yes?
Can you just say a little bit about what the intuition is?
Yeah, I will.
Why integer weights,
Ah,
why that bound works, but what doesn't quite go through for general weights?
well, I can give you a very high-level intuition right now. Maybe later I can give you a better intuition. So here's a very high-level intuition. If you don't have integer weights, you can hide complexity in the denominators of numbers, in a way. So it helps somehow to have fractional weights. So if you are allowed to have weights that are like half integral, this already gives you enough expressivity to compute the maximum of 5 numbers in 2 hidden layers. And more generally, this construction with logarithm to the base 3, all the weights will still be powers, all the denominators of the weights will still be powers of 2. And now, I guess if you want to improve this upper bound, you will need even more prime factors in the denominators. But whatever. I mean, I can. There's some results hinting that you need more prime factors in the denominators if you want to improve the upper bound. Yeah.
But your conjecture in the integer case, the theorem is unconditional. It doesn't depend on any complexity theoretic.
No, it doesn't depend on any complexity theoretic assumption. It's unconditional, yes.
I'm a little confused because you said the gap is between 2 and log 2 of them. But
Yeah, now it's not anymore.
Oh, I see. Okay.
Yeah. That was before this slide. It was before May 25. Yeah. Okay. So what's the main ingredient? I mean, I gave it away in the title of my talk. The main ingredient is polyhedral geometry. Some people would even say the main ingredient is tropical geometry, but I also had people from the tropical geometry community saying, oh, you're not really doing tropical geometry, so I don't dare to write this down on my slides anymore. So how does it work? Think of a continuous and piecewise linear function, like this one, which I showed you before. And now assume your function is convex. That makes things easier. Also assume you don't have biases. That makes things easier. So this function is convex because it's a maximum of a couple of things, so that's fine. What can you do? You can look at all the pieces of your function and look at the coefficient. Like in each piece you compute a linear function, you can look at the coefficient vector of this linear function. So in this piece it's 0, 0, in this piece it's 1, 0, and in this piece it's 0, 1. You take these and form the convex hull. What you obtain is a polytope. A polytope is just a convex hull of a bunch of points. And this we call the Newton polytope of this continuous and piecewise linear function. This term is borrowed from the tropical geometry literature. So they have these Newton polytope objects. You can also go the other way. So any polytope, given any polytope, here's the obvious way. You take the vertices and you take the maximum of the vertex transposed input, and that gives you a continuous piecewise linear function. Another way of viewing this is you solve a bunch of linear programs. So you have a polytope, which could be the feasible region of a linear program. You take an objective vector C. You look what's the objective value, and you map the objective vector to the objective value. That defines you a continuous and piecewise linear function, which is exactly the function you started with. And that's called the support function of the polytope.
essentially is the way in which the optimal solution changes depending on the objective function. Right?
Exactly. In the way in which the objective value changes.
Yeah, it's, the optimal solution in the sense of the value of the optimal
Yeah.
solution changes accordingly.
Yeah. And it also makes sense that it's piecewise linear because, as you may know, like a linear program has always a vertex as an optimal solution. There are only 3 vertices. As long as you stay with the same vertex, this dependence is linear. So that's why the function is piecewise linear in the end. Yeah. So that way we can go back and forth between continuous piecewise linear functions and polytopes. And it's some kind of duality in a sense. So you can also use LP duality to make rigorous statements about this correspondence. And the nice thing about this correspondence is that it is also compatible with a bunch of algebraic operations. So if you take your function and you multiply it with a positive scalar, this just corresponds to scaling the polytope. If you take your function and you add it to another function, this corresponds to taking the Minkowski sum of the 2 polytopes. So what is the Minkowski sum? That's like the Minkowski sum of 2 sets is just the set of sums of elements of the 2 respective sets. And finally, if you take the maximum of 2 functions, that corresponds to taking the convex hull of the 2 polytopes. And that makes this map basically into an isomorphism between convex continuous piecewise linear functions and polytopes with respect to these operations. Okay. And why is this cool? This is cool because you can use this isomorphism to prove things about neural networks, or let's say neural network expressivity. Because if you're interested in the set of functions you can represent, given some ReLU operations, you can as well look at the set of polytopes you can generate starting from some simple starting polytopes like points, applying operations that correspond to whatever a ReLU neuron does, using this isomorphism here. I mean, a ReLU is basically positive scalar multiplication, addition, and taking maxima. So for each of these things, we know what happens in the polytope world. So to convince you that this is really useful, I'm going to prove again the fact I proved to you earlier, which is that this function cannot be represented by a single hidden layer neural network. I'm not really going to prove it to you, but I will tell you how you could prove it in principle. Namely, if you look at the polytopes that are associated with neural networks with only one hidden layer, they will always be centrally symmetric. In fact, they will be zonotopes if that tells you something. But if you have a centrally symmetric polytope, okay, I mean, the easy answer is the triangle is not centrally symmetric. So you cannot generate this Newton polytope with a single hidden layer. And more sophisticated versions of that helped us to prove this lower bound for the integer case, actually. So we were arguing about some invariance of the polytopes associated with neural networks with a certain number of hidden layers. And these invariants kind of told us that, okay, you need logarithm to the base 2 if you have only integer weights available. Okay. And it also helped us to prove the new upper bound. And here's the little intuition I promised to you earlier. First of all, observe that the maximum of a bunch of things, what is the Newton polytope, it will always be a simplex. So a simplex is the higher dimensional generalization of the triangle. So in 3D, don't think about whatever happens inside, but in 3D, the Newton polytope of the maximum of 4 things would be this triangular pyramid here, this tetrahedron. So what can we do with this? I mean, I want to tell you that you can compute the maximum of 5 numbers and 2 hidden layers. That's what I would like to convince you about. And I'm not sure if I can give you a very high-level intuition of that. But the first thing I do is, to represent the maximum of 5 numbers, I would need 4 dimensions, because the simplex with 5 vertices is 4-dimensional. But now I'm in 3 dimensions because I cannot illustrate 4 dimensions. So I have the maximum of only 4 numbers, and we already know how to do this in 2 hidden layers. So you might say it's a little bit boring, but I think it still helps to show you the intuition. So what we do is we take this simplex and we cut it a couple of times into smaller polytopes. We subdivide it. That's what polytope people like to say. We subdivide it. How do we subdivide it? Basically, we take 2 hyperplanes and chop through it. And these are 2 very specific hyperplanes. And what we obtain is 4 pieces that look like this. So in this view, I rotated it such that all the vertices are like on the outside of this square. And here it's easier to see the hyperplane. So I chop here and here. And in the 3D, like in this, you easier see the 3D structure. So basically I chop here and then here, I think, like in the back. Yeah. But what I obtain is 4 pieces that are not triangular pyramids, but at least combinatorially square pyramids. I mean, this is not a square, it's a parallelogram, but combinatorially they are square pyramids. And now the cool thing is, like here's the intuition why this helps. As I said earlier, if something is centrally symmetric, or if it's a zonotope, but if it's centrally symmetric, we can more easily represent it with 1 hidden layer. And now we have this parallelogram here, which is centrally symmetric. So this part of this piece, of this chop of our polytope can more easily be represented with 1 hidden layer. And then we still have this apex. And we also have the other dimension, which I'm not even showing here. So there are some more details. But you can take this subdivision and lift it to 4 dimensions. And then you obtain something that really gives you a better neural network. That's the intuition behind it.
How can you see that it's better?
Better in the sense of you can compute the maximum of 5 numbers with 2 hidden layers. So in a way, in 1 hidden layer, you would take care of these square bases of the 4 pieces. And in parallel, you would take care of this vertex and the other vertex, which is not even shown. And then in the second hidden layer, you would combine these 2 things in a convex hull. That's kind of the high-level intuition. But I mean, I'm hiding lots of details here. So.
And dividing by 2 is corresponding to chop off the...
Yeah. So basically, we are kind of chopping through in the middle, and that corresponds to dividing by 2. Now, there are some results saying that if we want to do the maximum of 6 numbers with 2 hidden layers, we would probably need to chop into 1/6 or something like that, because we need 2 and 3 in the denominators of our weights in the end.
So the resulting figure will have 6 vertices?
The
chopped part will have 6 vertices?
No, way more. I mean, if you take this and you chop in by 6 in several dimensions, and this will explode combinatorially.
In the case of 2 layers. In the case
You mean this? Exactly this.
But you said it had 1 dimension more, no?
Yeah. So if we want to compute the maximum of 5 numbers with 2 hidden layers, then this corresponds to a 4-dimensional problem, because the convex hull of 5 points is 4-dimensional. So basically, the polytope I'm interested in is not this tetrahedron here, but it's a tetrahedron convex hull with another point that lives in another dimension. But everything interesting I do in these 3 dimensions, and the other point is just there to take the convex hull with. But this is only 4 vertices here, so it's 4 plus 1. Yeah. Yeah, that's the intuition. And yeah, as I said, so this geometric intuition helps you to represent a maximum of 5 numbers of 2 hidden layers. And then the logarithm to the base 3 bound can be obtained by, I mean, not only repeatedly doing this, but also like stacking, like you do this locally many times, and then you repeat this local doing many times. So this is like a double stacking kind of this thing, and then you get the logarithm to the base 3 as a general upper bound. Okay. That would be everything about the depth part. Are there questions? Yes?
Is there any way to restate your conjecture or your bound in terms of polytopes?
Yes. Yeah, you can inductively define classes of polytopes. So the first class would be points, the second class would be zonotope, the third class would be something like convex hulls, no, something like finite Minkowski sums of convex hulls of two zonotopes or something like that. So this would be an inductive definition. And then the conjecture says something about how to represent the simplex as a Minkowski difference of two polytopes that appear in some of these classes, something like that. There's a formal statement written down in some of my papers. Yeah?
Do you remember how many neurons are in each layer, hidden layer?
For this construction specifically, like for the maximum of 5 numbers, I think it's like less than 100, but more than 20 or 30 or something like that. It's basically, in the end, a sum of 8 terms of which you can easily see that they can be representative of 2 hidden layers. But each of these 8 terms also needs several neurons to be represented. But yeah, you can pull this back into an explicit representation that's, I mean, not that much fun, but at least you can look at it as a human. And you can also prove, like, you can prove that all this works without using geometry. That's not I mean, the geometry is there to develop the intuition and to develop the result, but then if you want to prove it, you don't need the geometry, actually.
But it is an intuition that you wouldn't be able to kind of follow if you did it the other way.
Exactly, yeah. Okay. Polynomial size. So now I don't care about the depth anymore. I'm really just interested in the overall size of the neural network. And, okay. I mean, I have this connection to polytopes, and this is going to be useful again. So I rather use some polytopes that I understand well. And these are polytopes that come from combinatorial optimization. So if we want to analyze which problems can we solve in polynomial size neural networks, this is kind of the same question as asking, are there familiar problems of which I already know they can solve them maybe in polynomial time and other models of complexity and pull them to neural networks somehow? So here are a bunch of positive, I mean, maybe something which I don't mention on this slide, but which is maybe good for this audience to mention is, I mean, Bellman-Ford, for example, is just like minima and sums, and that's it. So we can easily do that with a neural network, because minima are easy, sums are easy. Okay. So Bellman-Ford would also be an example, or shortest path, if you phrase it as a problem, which you can easily represent as a neural network. So 2 things for which this was non-trivial are on this slide. So you take a graph. Here's finally a graph. I don't draw a graph, but there is a graph. And you want to know what's the minimum spanning tree of that graph, depending on the edge weights. And that's a continuous and piecewise linear function, because it's just like the minimum of a bunch of sums of the edge weights. So this is a continuous piecewise linear function, but it has like many, many pieces, because it has 1 piece for each tree. So it's not so trivial how to make a neural network out of this. But in the end, we were able to do this. So we constructed a polynomial-sized neural network that does this. How do you do this? You need to basically come up with an algorithm that only uses minima, maxima, additions, scalar multiplications, and that's it. In particular, no if branchings or anything. Branchings are difficult to realize. Or something, I think someone said this week something like argmin is difficult to realize within a neural network. That's exactly what's happening here. So you can easily compute a min, but not so easily compute an argmin, or something like that. And we did the same thing for the maximum flow problem. So given a directed, let's say a flow network, and you want to map the arc capacities to the maximum flow between the source and the sink, that's also a continuous piecewise linear function, and we can also do it with a polynomial sized neural network. So one might think, are there any limitations to that? Maybe some negative results we can prove. Or what about other problems for which we know that we can solve them in polynomial time, like minimum cost flows, matching problems, linear programming? I mean, yeah. That's maybe why I was so interested in Christopher's result that you can do interior point methods with graph neural networks. Yeah, and as I said, are there any problems for which we would expect that we can do this and we cannot do it? Are there any lower bounds we can prove? And here's my attempt to prove lower bounds. So my intuition is there must be, like this seems very restricted, like just maxima, minima, some scalar multiplications. There must be something which you cannot do. And here's my intuition. This comes again from linear programming theory. And it uses a notion that's called the extension complexity of a polytope. So here is a polytope, this octagon here. Its extension, okay, so first of all, if you want to represent this octagon as a linear program, you need 8 inequalities, right? Because you have 8 facets. Now what can you do? Well, you can take a 3-dimensional polytope that projects to this octagon and has only 6 facets. I mean, if you look at it, you can convince yourself that this works. This polytope up there has only 6 facets. Now, what does this tell us? This tells us that if we introduce a third variable, a third dimension, a third variable, then we can realize this polytope with fewer inequalities. And now the extension complexity of a given polytope is the minimum number of inequalities I need in any higher dimension to get a polytope that projects down to my original polytope. And that quantifies how complex it is to represent your polytope as a linear program. Okay. And why do I think this is useful to prove lower bounds? Well, because people have proven lower bounds on this quantity for interesting polytopes. Like, if you look at the matching polytope, which is basically the Newton polytope of the function mapping edge weights to the weight of a perfect matching, of a minimum perfect matching or maximum perfect matching, whatever you want, or the TSP polytope, then people have proven exponential lower bounds on this. And in particular for the matching polytope, this is very surprising because min-weight perfect matching is something you can solve in polynomial time. Still, you cannot write down a single linear program solving that problem in polynomial time. So maybe this.
You mean a compact linear program, right?
Yes, of course. I mean, you can, of course, write down an exponential size linear program. Yes, that's for sure. Yeah. Right. Thanks for this addition. So maybe this can be used to also prove similar lower bounds on neural networks. Because the models of computation, they look a little bit similar. I mean, basically, yeah. I wanted to do this. So here was my dream result. My dream result was that I can somehow bound the extension complexity of a polytope polynomially in what I call neural network complexity of the polytope. The neural network complexity would be the number of neurons I need in order to represent the support function of the polytope. Like support function is what I showed on this one duality slide. Yeah, so this was the dream with which I started. And then the problem was this seemed to be hard to prove. So what do you do if you want to prove an inequality and you don't manage to? Either you make the left-hand side smaller or you make the right-hand side bigger in order to find something that you can prove, right? So let's do both. How do we make the right-hand side bigger? Well, we look at special cases. We look at neural networks that don't have the full power of all neural networks. Then we need more neurons, potentially. And one very natural option to do this is to disallow negative weights, because negative weights are somehow the thing that makes problems if we want to prove this thing. And actually, neural networks where some or all weights are restricted to be non-negative have been looked at. So they're called monotone neural networks, or even if you look at it, there's something like input convex neural networks, if you have heard of it. So this is a quantity people might be interested in. And the other option is to make the left-hand side smaller. So we do something that is a little bit more powerful than the usual extension complexity. And here it turns out that Minkowski sum is the thing we need to look at, the thing that makes things difficult. So instead of finding extended formulations of P, we find extended formulations for two polytopes Q and R, which satisfy this equality. So basically P equals R minus Q, but I can't write it like this because Minkowski sum doesn't have a natural inversion. So I write it like this. And this is a quantity that's at most the Minkowski sum because the extension complexity, because I can always choose Q to be a single point, which has extension complexity 0. So this really makes the left-hand side potentially smaller. I mean, definitely not bigger. That's what I want to say. OK, so now I said I want to prove this inequality. I want to either make the left-hand side smaller or the right-hand side bigger. Now I did both, but I don't do both at the same time. I do both separately, and I obtain two results. So either I keep the left-hand side, I relax the right-hand side, and I can prove the extension complexity is a lower bound of the 2 times the monotone neural network complexity, or I replace the left-hand side and keep the right-hand side, basically, up to a factor of 4. And both of them can be proven. What do we get from that? Well, one conclusion is that the neural networks captured by this quantity, like monotone or input convex neural networks, they require exponential size to solve matching or TSP exactly. Or even for matching, like I think for both of them, you can even prove some approximation result in the sense that even if you want to approximate these problems, you need exponential size because people have also studied approximate extended formulations. Yeah. That's basically a corollary of the first step. And the second step is a little bit less clear what to get out of it because we don't understand this virtual extension complexity very well. But yes?
Just a quick question for clarification. So you said matching, I can actually have a polytime algorithm to solve it, just the polytope is hard to describe.
Yes.
If you could the neural network simulate that algorithm, just not be expressing the support function of the polytope. That I mean, does this mean that the neural network cannot solve the thing at all?
It means it cannot solve it end to end, of course. I mean, of course, there might be other way of using the neural network to solve the problem in the end. Yes, I mean, yeah, it's more a statement about like the expressive power of the neural network itself, and not so much about the way you can apply the neural network. Does this make sense? Kind of. Okay. Yes?
So, just trying to understand the corollary. So does it mean that input convex neural networks are, from my understanding, convex functions of the input, right?
The input convex neural networks, basically in the first layer you can have negative weights, and the other layers you cannot.
So you end up with a convex function.
Yes, you end up with a convex function.
So does it mean that the corollary that you're representing a non-convex or hard problem with a convex approximator of an exponentially higher?
No, I mean, the support functions are still convex of these polytopes. So this is not an issue of convexity here. Like everything, like all the functions I look at are convex in this case. I mean, sure, if you have non-convex functions, you can certainly not express them with an input convex neural network, but that's trivial. Yeah. Yes?
So if you would extend your neural networks with max nodes, right? So like I can not only do addition, arithmetic, but I also can take a max.
Yeah, so actually all these results are phrased for max out networks where you can exactly do that.
Okay.
Which are like more general than ReLU neural networks. I was just not mentioning this because, yeah. For the depth question, this of course makes a crucial difference. But here, since I'm like basically ignore polynomial factors, I don't care about how many, like what's the fan-in of my max neurons or something like that. This all doesn't really matter here. Okay, more questions? Yes.
Yeah, this is a follow-up, but I'm like, what I'm trying to understand is I can use this, sort of ReLU to simulate and or. And so
Yeah,
if
right,
I have
yes.
a polynomial time algorithm, I have a polynomial time
Yeah.
circuit. So
Yeah.
what am I not getting between this corollary
Yeah,
and
yeah.
that construction?
Yeah, it's a subtle difference that depends on the model of computation. So if my numbers are represented as bits and I give it to my neural network as bits, then of course I can simulate and ORs, so I can simulate all the Boolean circuits and solve all the problems in P. However, the thing is that this is very non-robust to small changes of the numbers because like the bit representations could change drastically if you just do small changes. So in this model, we look at neural networks that obtain the plain real numbers as an input, and this is a real model of computation, so there are no bits, anything. And that makes the model different. I wouldn't say like harder or easier or something, but I would say in a way it's like further away from practice, because in practice we always have bit representations. But in another way, it's closer to practice, because we would never give our neural network a bunch of bits. We always give them, like intuitively, we want them to be like robust to small changes. So it makes sense to look at the inputs in terms of real numbers, and then this model might again be closer to practice. I mean, you can discuss this, but it's like basically the model I'm looking at, which is different. Okie dokie. I can say 2 minutes about the 3 steps to prove this. I mean, not to do the full proof, but what can you do? You take your general neural network, and you can basically split it into 2 monotone neural networks. That's a procedure that you can write down. It's also related to like these results talking about tropical geometry in neural networks. They basically do the same, but like in a little bit different phrasing. So that way you can split your neural network into 2 monotone neural networks, which are not much larger than the original neural network. That's step 1. And you only need it for the second result, because in the first result we already assume that our neural network is monotone. And then for monotone neural networks, we basically can read off an extended formulation, not of the polytope itself, but of the epigraph of the function. What is the epigraph? It's a set of all points that are above the function computed by a neural network. And the neural network is like basically if you go through it layer by layer, you can read off an extended formulation of this epigraph. And then linear programming duality gives that the extension complexity of the epigraph is actually the same as the extension complexity of the polytope. If you put together the second and the third step, you obtain the first result. If you also combine it with the first step, you obtain the second result. So these are the 3 steps. Like each of them is quite doable, but plugging them together gives these 2 inequalities. Okay. This I will make very short, but I mean, there's this quantity appearing here, which is the virtual extension complexity. And how could I make my dream true? By proving that virtual extension complexity cannot be much smaller than the actual extension complexity. And the virtual extension complexity is defined by a Minkowski sum. Here's an example of a Minkowski sum. So if I take this parallelogram and I add a triangle, what I can do is I basically slide the triangle over the parallelogram and I see which points I hit. And that's an illustration of the Minkowski sum of the 2 things. And the important observation is here that linear programming is basically compatible with this Minkowski sum. So if I optimize over the Minkowski sum, the objective value will be the sum over the optimization problems over the summons of the Minkowski sum. So what does this tell us? It tells us that in order to solve the linear program over P, it's sufficient to solve the linear programs over Q and R, because I can just subtract the objective values. Yeah, this is what I just said. So if we have compact formulations for Q and R, we can efficiently solve a piece over P. So in a way, this virtual extension complexity captures the power of differences of 2 linear programs. I mean, earlier I said extension complexity captures the power of 1 linear program. virtual extension complexity covers the power of differences of two linear programs. Now, I guess this is a question that would be interesting to the combinatorial optimization community is, the question, like the openly phrased question is how much smaller can this virtual extension complexity be compared to the extension complexity? And there are two possible answers. One is it can be much smaller, but that would be cool for the combinatorial optimization community, because then we can say something like, okay, the difference of two linear programs is actually much more powerful than just looking at one linear program. And the other option is no, virtual extension complexity cannot be much smaller than the extension complexity, but then we have basically proven the dream in the sense that we have lower bounds on general neural networks and not only on monotone neural networks. So answering this question, no matter what the outcome, I would always find it very cool, but I don't know which of the two options is true. Maybe someone of you can tell me, I don't know. Yeah. I guess that concludes my talk. The two main takeaways are Polyhedra are a cool tool to understand neural networks. And many things, I basically almost only talked about open problems. So join me solving them. These are my two main takeaways. And then if you find this cool, there's going to be a workshop in Nuremberg in March 26. You're invited to come. You can either scan the QR code now or go to my website and from there to the website of the workshop anytime later. If you like that stuff, or also if you have, even better if you have other ideas how to apply Polyhedra to say something about neural networks, I would be happy to see you there. And that concludes my talk. I'm happy to take more questions.
Yes.
Yeah, thanks for the great talk. It's really nice.
Thanks.
I was wondering if this can be extended to, let's say, GNNs to improve lower bounds. I mean, it's an obvious question.
I was totally expecting this question.
I know, yes. That's why I also asked this weird question, because GNNs are basically the computation graph of GNNs are basically some layer-wise DAG, which is not...
I understand. Yes, I mean, my first intuition would be exactly what I replied to your earlier question, that if I prove some lower bounds on these neural networks, this should also give me lower bounds on GNNs. But nevertheless...
But you want some more graph structure in there, right?
Yeah, over the course of the week, I thought, like, maybe there's some cool way to combine this polyhedral perspective with the GNN perspective, the Weisfeld-Lehmann perspective or whatever, to say something about, like, if I have a GNN that has these many iterations or these features or whatever, then I obtain this set of piecewise linear functions still. Like something like that. I'm not sure how much of that exists, actually. I haven't done the research, to be honest. But it would be cool to do that.
I think you can if you basically take it to the tropical geometry stuff, which you said you didn't want to do.
Well, I didn't, I mean, I said I don't want to call it like this, at least. I guess, like this polyhedral world is basically putting it to the tropical geometry world, isn't it? Yeah.
But I know you can, because every GNN is also tropical. I mean, that's what I'm working on proving.
Okay.
I know it's true.
Yeah, cool.
So understand and improve it.
Yeah.
Once you do, you basically have a framework for everything in tropical geometry.
Yeah.
And this works.
Okay, that's cool to know. I mean, I would be curious to learn more about the details.
Yeah. I mean, we should.
Yes, let's do that.
I also had a question. So did you do experiments running these things? Because you have all these bounds.
Yeah.
Do you know if they're tight?
Like, basically, like much parts of my talks were about the fact that I don't know that most of these bounds are tight. The problem about
experimentally, do you ever see that sometimes
they're
no. Achieved,
the thing is, I think it's pretty difficult to set up experiments that like are close to these theoretical statements somehow. I mean, because we are talking about these exact representations, and then I mean, you can of course get something like, okay, in the experiments it looks like we need some logarithmic depth, but I don't think it tells you something about the theory really. I mean, could have could be many reasons somehow.
Yeah, no, I'm just curious because there's this other paper by Lekheng Lim and some of his collaborators on the tropical geometry of
Yeah.
neural networks. And I mean, recently with my group, we did some experiments because they have an analytic upper bound for the number of linear regions as a measure of expressivity.
Yeah, okay, yeah.
And we saw that like almost rarely this bound is achieved, right? So,
Yeah, I think this is something.
yeah, so, I mean, I know your setting is a bit different here, and you know you're sort of studying
Yeah.
different things in linear regions.
Yeah.
But I'm still just curious because
Yeah.
this was the thing that we were just spent like a lot of time doing experiments for, and I
Yeah.
was just wondering if you something similar.
Yeah, no, I'm. My research hasn't been very experimental lately, but I'm always. I mean, yeah, it's cool to hear that there are some nice experiments that you can do, I guess.
So you mentioned that when you were computing the minimal spanning tree, you had to avoid the branching.
Yeah.
Can you say a little bit like how you avoided doing that?
For the minimum spanning tree case. Basically, we came up with a tailored algorithm for the minimum spanning tree problem that didn't use branchings. So, in a way, what you can do is you look at your graph, you select one node, you remove that node, and now you need to update all the other weights in a way that the value of the minimum spanning tree of the new graph still tells you something about the value of the minimum spanning tree of the original graph. And you do that again and again. This is related to, like, this is basically a tropical version of what people call the star mesh transformation in the electrical networks community. So there they also have a transformation to remove one node from the network step by step. And that's called star mesh transformation. If you tropicalize this, then you obtain this algorithm.
Are there any results in complexity theory that can help you with any of this? I mean, you're proving lower bounds and...
Yeah. Yeah. I mean, I think what you need to look at is arithmetic or algebraic complexity. So you look at circuits that can do something like addition and multiplication, and then usually they compute polynomials, and then you can tropicalize this, and then you basically obtain neural networks. So there are some relations. But the thing is, in a way, neural networks have extra power in the sense that they can do these scalar multiplications, which don't really have a non-tropical analog, and then also, at least not one that has been studied in the complexity, circuit complexity community. And then also, yeah, so there, I mean, okay, the short answer is I don't know, like, concrete implications, but it still feels very connected to this algebraic complexity world.
I have questions, but I think we should postpone them because we still have one talk. Thank you very much.
Thank you.